So yeah, I thought I'd put a background to make people feel at home. Um, if you guys don't have to all turn off your video. I kind of like seeing a little bit of video because then I know that like, so the hard part about doing a presentation on a Zoom is that you get zero feedback. So like every joke falls flat and you have no idea if people are actually like asleep or awake or not. So I like it as much as possible if you guys are willing to. There we go. We got claps. The emojis work really well too, actually. So feel free to do the emojis or thumbs up and stuff. I kind of like that when I'm speaking. And relative to that too, I also really like it when people ask questions kind of on topic. Like, so if at any point you have a question, please do send it to Daniel in chat. If we had a fewer folks, we might just unmute everybody and ride the chaos, but it's too easy to talk, I think, over people. So let's kind of get into this real quick. This talk is, you guys selected this. So to be clear, there were several different topics and this was chosen by you. This is talking about binary reverse engineering with intermediate languages. And it's full disclosure. I am one of the developers of Binary Ninja. I make money when people buy Binary Ninja, so take that bias in mind. I'm of course going to come at this from Binary Ninja's perspective, but I try to be as fair as possible, and I'll tell you what the kind of the strengths and weaknesses are for everything. Here's my bio. I wouldn't worry about that. I'm actually more interested in what you guys are. So I see by a show of hands, and this would be great. We can do this in the emoji thing, I think, here. So figure out what your emoji stuff is. Who here has done binary reverse engineering? See if there's like that. There we go. Yep, throw up the hands. You can do actual hands or emoji hands, either one. Excellent. So either most people are still trying to find that button to do it, or we've only got a couple so far. There we go, a few more. Who has used a decompiler? Throw up a thumb or a hand for that one. All right, who has written code to automate reverse engineering? So if any did any kind of plugins or any automation that would do reverse engineering. We've got similar kind of audience so far. Who's used an IL or an IR for the reverse engineering? So either you've written code or you've like specifically looked at an intermediate language or you've used it behind the scenes in some analysis. Okay, so this is actually a trick question because where is it? Oh, I skipped past it. Because if you've actually done, if you've used a decompiler, you've actually also used an IL or an IR for reverse engineering, right? So this is a little bit of a trick question, but pretty much every modern decompilation tool out there uses some sort of IL or IR kind of behind the scenes. And if you ever kind of take a compiler's course, you may also have done some work with intermediate languages. And then I include this last one just for the truly high end. If you've published research leveraging ILs. So as I mentioned a second ago, I was visiting ASU a few weeks ago, and there was like 5 people in the room that like raised their hand when I asked this one. So that's when I know that I'm going to get really good feedback on my talk. So okay, so here's the outline of the talk. And again, at any question, interrupt and ask questions, Daniel, because I like to know that you guys are with it and paying attention, and you have things that you're thinking about. So we're going to talk about what binary analysis is, why we would use intermediate languages. We're going to overview of a number of different ones. Then we'll show a couple of demos. I think in this case, actually, the demo I'm going to show, though, is Binary Ninja's high-level IL, because that's usually a little bit more interesting for that one. But I'll let you all vote on that. So first, what is binary analysis? So let's first talk about what compilation is, right? So when we talk about compiling binary executables, we start with source code. We compile it, or we parse it rather, like say YAC or whatever, into some sort of AST. And then we're going to take that AST and we're going to do some transformations on it. And we're going to get an IR. We're going to do some more transformations on it. And then we're going to take that IR and we're going to get machine code. There may be a few other kind of steps in that process, but if you've taken a compiler's course, this is sort of like the basics of many of how modern compilers work. So decompilation, sometimes called lifting, is the reverse. It's the opposite. It's taking the machine code and going back into source code and potentially through a similar kind of process in reverse. So to be clear, when we talk about binary analysis, there is 2 sort of general schools of binary analysis, like static versus dynamic. I would love some feedback from the audience. Does anyone want to answer a quick summary of either static or dynamic analysis, right? So Daniel will just message that answer to Daniel in the chat, and he'll read out the first person to get it right, and they will get virtual emoji, claps, accolades, all the internet points. Static, or you pick one. Like if you go now, you get to pick either one. If you're second, then you have to you've only got one left. So as soon as possible, get your answers typed in there. Static or dynamic. And I'll give you a preview that we're only really going to be talking about static for this course, but dynamic is equally viable and useful as a binary analysis technique. Do we have an answer yet?
We do not have an answer. Oh, we got one. Okay.
Oh, good.
Static analysis involves reviewing the code and assembly without running the binary, while dynamic analysis involves debugging and checking how it works in runtime. So
yeah.
Oh, it was by Owen, by the way.
Excellent answer. It's a great summary, and that's usually exactly the easiest way to differentiate. It is, are you running it or are you not? So then we get some weird questions like, well, what about a symbolic execution? What about emulation of an IL? You know, some other like kind of gray spots maybe in between that we could quibble over. But pretty clearly, running something in debugger is dynamic, and opening up and looking into static dead listing in disassembler is static, right? And so there's flavors, but we're primarily just talking about static analysis. Okay. It's really important that I clarify for you guys why binary analysis is not the same as source analysis, right? So there are, I mean, actually, I know of literally like, there was a team that submitted to the DARPA CyberGrind Challenge. I was helping to do like the visualization side of that. And one of the teams that participated was basically like, well, we're just going to take all the binaries you give us, decompile them with IDA, and then poof, run all our source code analysis on it. And like everyone kind of looked at them like, well, that, you know, like, it's not going to work, right? And they were like, no, this is going to work. This is like, you know, an actual real company and a person with a PhD who said this. And like, we're like, no, like that's a terrible idea because like one, decompilers break a lot. Two, you miss a lot of information about like the whole state of the binary when you try to decompile, because decompilers are really meant to go function at a time. They're not really meant to decompile an entire program and just have it be work and be accurate. And they just like, they get stuff wrong. Like there's just an error rate. So like at every layer of these translations from machine code up to source code, you have the potential for error. And so anyways, yeah, their approach failed spectacularly. And then this is a quick summary of why that's the case, right? So here's some of the things that compilers make really hard. I'm not going to go into great kind of detail on this unless you guys have any questions. Feel free to ask any questions about them, but I'm going to kind of blow through these. Suffice to say that compilers do stuff that make recovering information in the source code really difficult, right? And that's probably not a surprise if you've done any kind of binary reverse engineering. At the most obvious level, I like to point out comments, right? Like when you have source code and you have comments and you have function names, like that make things understandable, they help you as a human know what's going on. When you compile it into binary form, those are gone. And maybe you've got debug symbols, but rarely, and even with those, there's still things you're missing. You don't get the full source. And so trying to like accurately produce this has a lot of issues. So for example, these are questions that I think people take for granted. So when you open up IDA or Gita or Binary Ninja and you're analyzing a binary, you just want to look at all the functions, right? Like you usually don't want to start you might maybe want to look at strings. So maybe you want to look at all the strings, and then maybe you want to look at all of the functions that call those strings, or maybe you want to see, are there any functions that are the names of, did I match any static libraries? But like you sort of assume that the tool has already found all the functions, all the strings, and maybe all the pointers, right? Like where are these things in there? And these are actually very, very difficult. These are fundamentally undecidable, actually. And here's a really good example of this. If I give you a binary and I say, where does all the code go? Like, where's all the code? Well, that's actually really just the whole thing problem, right? Because if you knew where all the code was and when it's the same as saying, like, when is it going to stop? You can't actually know that. I can just, for example, take a binary that reads in user input and then takes that input and writes it to a data buffer and executes it. Well, if you don't have the input, you of course don't know what that program can do. These things can literally do anything. And so it's actually difficult in the general case to perfectly solve this. Now, the good news is compilers are fairly reliable. And there's like ways that we can kind of get around it. We can do a pretty good job of recovering this, but doing a perfect job is very difficult and almost shouldn't even really be your goal. You really should have a system that instead of trying to aims to be perfect should fail gracefully and should be able to work with what it can and let the user inform the analysis. So that's actually, I think, one of the things that IDA Pro and Hexrays maybe don't get enough credit for, is that we kind of take for granted now in this industry that like you as a user would use a tool and you would help improve its analysis. You would add types and names and comments, and it would inform the analysis and improve the rest of the decompilation or the disassembly. And that's actually something that wasn't really a thing that people thought about really until IDA has done it. And now we just sort of like assume, well, of course, that's how you do that. But that was actually a rather key kind of insight, honestly, I think that they had. So if you look at the I in IDA as interactive, right? That's literally what it stands for. And it's actually pretty important. Okay, there's a lot of ways that this stuff fails. Compilers do weird things. let's talk about like one of my major kind of like theses on intermediate languages, right? Like, why would we use IL? So that's what I'm trying to convince you of here. And so first, I'm going to use IL versus IR. First, by a show of hands, I would like for people who think there is a clear distinction, and they would define IL and IR as different things, to raise your hand. So in the chat, do your chat emoji. And if you think they're the exact same thing and you use them synonymously, then raise your hand. So if it's synonymous. And then for everyone who's just not ever going to respond, raise your hand now. Sorry. Okay. So there we go. Good. One honest answer. I like it. This is actually a thing reasonable people can disagree on. In fact, I happen to use them synonymously. I think that it's worth calling IL and IR as the exact same thing. And Peter LaFosse, one of my co-founders of X35, thinks that he likes using them to mean different terms. So he would use intermediate language for something that is actually a language, right? So when you do like program, like computer science as like the science side of computer science, languages have properties and there's a lot of study into like designing languages and features of languages. And a representation, like a language is typically like complete, right? And representations are just like, it's just a thing that represents it. It doesn't say any guarantees about whether or not it's language or not. That said, I'm going to use them interchangeably throughout the rest of this talk. But you're welcome to quibble if you prefer that. I'm happy to disagree. Okay, so in fact, you'll actually hear more terms than that. So these are all terms that get used for the exact same thing. You'll hear intermediate language, you'll hear intermediate representation, those get abbreviated IL and IR, bit code, VM opcodes, and P code. So P code, a lot of people are familiar with as the name for Ghidra's intermediate representation. That's not actually like the sort of like their specific name. It's actually a generic name that was used in research prior to their publication. They just like that name, and so they used it. It's actually more of a generic term than the name for Ghidra's P code. In fact, there's even other tools out there that have released intermediate representations called P code that are not Ghidra before they were public, because again, it's just kind of more of a generic term. But you see like .NET and Java, they all have different names for their bitcode or bytecode or VM opcodes, like all that stuff. It's all a similar thing. It is a sort of virtual instruction set that is not machine code. It doesn't run in any actual real CPU, but it like maps kind of to maybe what like a sort of virtual machine might do. Right? So that's kind of what I'm going to use for these. So this is like the overall like thesis. This is my premise of the talk. And if you agree with this now, then I don't have to continue. You already believe it and I can stop. But this is my hope is that by the end of this, if you don't agree with me yet, you will, which is that reverse engineering is fundamental to understanding how software works. Like, I think that one's pretty easy. Most people are like, well, yeah, like if I have a binary, I want to understand what it does, I need to reverse engineer it. Right, sure. Intermediate languages are fundamental to how modern compilers work. Again, not controversial. I think most people would agree with that. The last one is a little bit of a leap, but I think it follows really naturally, right? The idea is that we should be using intermediate languages, therefore, in reverse engineering. Like if it takes a compiler to use an intermediate language to go one way, we should be using them to go the reverse. And I think this is probably fairly obviously true. Most people would agree with it. We'll talk a little bit more about kind of the whys of that. But that just means like we're using the same tools and compilers to go one way to go backwards, right? Okay, so here's some other advantages. Here's like the real reasons, like practically speaking, why would you actually use an IL? And I said often here, because this is not always true, as you can see below, but it's usually a much smaller instruction set. So when you have a physical CPU, it's often like very complicated instructions if they want to optimize for that. Even architectures that are RISC, right? What's the R in RISC stand for? Somebody in chat, quick. First answer gets kudos. I'll have to start bribing y'all, like mailing out Ninja stickers or something for good answers if we're not getting enough responses. What's the R in RISC? R-I-S-C. You can Google, like you're at home. You don't lose points for Googling or using your phone to do it. Like it's allowed. The R stands for, oh, somebody messaged me. All right, good. What do we got? Chat, there it is.
Sorry,
yes.
I messages too, but.
That's all right. Nick got it. Reduced. The R stands for reduced, right? So theoretically, it's a reduced instruction set. It should mean that there are fewer instructions in a RISC architecture. ARM is typically called a RISC architecture. That is obviously completely and utterly not true, right? Like 424 instructions as of ARMv7. ARMv8 even has more. So like, no, you don't get to call that like a reduced instruction set. But theoretically, ILs and IRs should actually have reduced instructions. And that's almost always true with the exception of VEX. VEX is a little bit of a strange beast. It has a lot of instructions. But if we look, Ghidra with P code, IDA's microcode, RISC-V is one of the very few native architectures that actually is really reduced, right? Like 72 instructions, that's really small. It's smaller than even Binary Ninja's smallest IL set. So like they actually stuck to the name, which to be fair, they have RISC in the name, so they ought to. MIPS is okay, it's really small, but then again, you get into like ARM, and you get x86 is just a monster. Depending on how you measure it, it has a lot of instructions, right? And so not even getting into like all of the extensions and crazy other stuff that you can get on that. So, and it does depend on how you count kind of forms and stuff. So you can definitely see the trend of like intermediate languages tend to have less, native tends to have more. Why does that matter? Well, because if you're writing code to parse something and you want to like analyze a binary, you want to build some tool to do reverse engineering, well, the fewer things that you have to handle, the better, right? Like if you have to actually handle every native instruction case, that's a pain. If you've got over 1,000 possible instructions, you've now got to correctly decode. You could use something like Capstone, or you could use some other library that kind of does it for you, but you've still got to now like parse the decoded object. You've still got to make decisions about it that may or may not map cleanly to a really simplified kind of instruction set. The biggest one though, is that it's architecture agnostic. This is the most obvious one. Would you rather write your plugin to either, find vulnerabilities or do some malware analysis, detect if something's bad, or whatever other reverse engineering purpose you want to do? Would you rather do it on all of these architectures, or would you rather write it once on an IL and just have it work, right? I think most people, it's a fairly obvious question. So that's the other thing about this last chart is even if you look at like, oh, RISC-V is not bad, MIPS isn't bad. Well, yes, but also if you have to write for each architecture specifically, you got to sum up now. You got to, everyone you want to handle, you've got to add now a whole new instruction set. If you write to an IL that supports multiple architectures, you write it once and you're done. It's much, much easier. You get a whole lot sort of more bang for the buck. There's also the fact that it really simplifies a lot of analysis. So here's just a little code snippet that a friend of mine actually wrote when Binary Ninja like first came out. He was like, this is like 4 or 5 years ago. Was really excited. He was like, I'm going to do a plugin. I'm going to show people you got a cool API. And he's like, I'm going to annotate syscalls on this. It was an Android binary that he had, right? So he has some Android binary, and he wants to pull out the actual syscall number from the syscalls. So like, there's this instruction that's like the service instruction on it's how Android does service calls, and you have to look at this register, and the compiler set it at this argument or this instruction kind of before it. And so that was his code that he wrote up. He's like using Binary Ninja to like look through it, and we're like, cool, good. You found the API and used it, but like, that's like the IDA way of writing a plugin, right? Like that's the, like, I've got this assembly way, like you should be using the IL way. And he's like, what do you mean? And we're like, well, like consider this instead. Just iterate over all the IL. If the operation of the IL is a syscall operation, so you're now just like comparing a type. And so first of all, it's also faster too, because you're doing string compares. It's much, much quicker if you actually want to like scale this up over lots of binaries. And then even better, there's also another thing that's kind of hidden behind this second one, which is there's like .params. Like the reverse engineering tool and the IL actually has a concept of like syscalls have parameters. And so like you could just query it. You don't have to know for whatever architecture this is, where does the syscall number come into play? That's literally just built into the IL. It does that for you. And so, oh yeah, also the same snippet that you now wrote here in ARM could now work in some other architecture. As long as it uses syscalls, like you would get the same kind of thing. You have the table of syscalls you're going to annotate maybe, but it's much kind of cleaner to do. So you can see kind of where stuff like maps in.
I have a question.
Yes, good.
Isn't there some loss of representation when converting to an IL compared to native assembly for the architecture by Ben?
Yeah, there is, and that's a fair point. And it depends on the IL how much of a kind of loss of fidelity you're getting. But that's absolutely. So when I talked earlier on about why you don't get to say like binary analysis means just decompile it and analyze it. Well, decompilers have problems, and one of the reasons that is anyway is that like at every stage of translation where you start with like zeros and ones, the CPU executes, like that's ground truth, right? Like the CPU is going barring CPU bugs, like for the most part how the CPU is going to handle that original bit of code, and then every time you do some sort of translation, a higher level kind of analysis, you have the potential to introduce errors. So that's absolutely true. There are some situations where, like if accuracy really matters, if you want to build an emulator, building an emulator on top of an IL is potentially harder than building an emulator on top of like the native machine code, because now you've got to like both parse the IL into the machine code into an IL. You've got to get the semantics right of every instruction you're lifting, and then you've also got to have the IL actually or your emulator handle your IL better. So it is potentially more complicated, yeah. But I would submit that there are very few situations where that outweighs the benefits. And it's also fixable too, right? Like if there are errors, you can fix them. And then in the end, you're going to be left with a better result if you've just done a good job QAing and testing. And there's some nice ways you can do that too with IELTS. In fact, absolutely. Oh, I didn't even notice this. This slide actually has the second bullet point, which is abstractions increase errors in translations, right? And so like exactly that point I was just making, that the higher level we go. And so this is sort of like just a cautionary tale. So like Binary Ninja is actually just about to release our decompiler. And there are still really good reasons why you might want to do your analysis on one of our lower level ILs. And that's exactly, that question is exactly part of it why. We have a low level IL for that reason. We specifically expose something that's closer to the machine code so that can happen. Does that mean you have a question if you got the hand up or?
No, I don't have a question.
Okay, all right, I just had like all right. Feedback, I like it, okay. Yeah, feel free to interrupt. So good question. All right, so some problems essentially with decompilers. Another thing that I like to point out too is I actually don't think C is necessarily the right thing. Like every decompiler is like, let's get back to C, just because C has produced more machine code than any other language in the last 30 years. But I don't think that necessarily means that C is the right way to represent things. At an obvious level, if somebody writes some Rust, compiles it, and then you decompile it back to C, you're probably not going to do a very good job representing what they wrote in Rust, right? Like you probably would actually rather have it look like in Rust. So that's kind of obvious. But even beyond that, even for things that were literally written in C or C++, there may be things that you want to like show that are not expressible easily or cleanly in C. Great example being stack layout, right? Like when you write some C, there's some things that are generally true about where variables are going to be, but they're not always true. Depending on your compiler optimizations, they may change dramatically, right? So the same source code with different compiler optimizations will result in dramatically different stack layouts and different control flow and all sorts of different stuff. With a binary, you may actually have kind of more information than it would be expressible in native C. And so you might actually choose your representation to be something else. You might actually want not C as the thing that you do your kind of analysis on. Some other kind of good reasons that you talk about, like relationships between variables, when things are used as temporaries and when they're not. Like there's things that you may know based on machine code that C doesn't really show you. Okay, so that's all the like why I would suggest ILs are good things to work with. Let's actually just talk about like, okay, great, I want to use an IL. Like what are my choices? What are my options? The subtitle here is Too Many Secrets. Anybody get that reference for people who like movies? It's getting to be an old movie at this point. Too Many Secrets, C-Tech Astronomy. What's the movie? Nobody? Somebody's got it. So, really? All right, come on, Jeremy. I see you typing. You got it. Yeah, I know you've seen this. There it is. Is that the answer to you I was looking for? So, Jeremy says Sneakers. That's right. That's the movie Sneakers. You should definitely. It's actually one of the better hacking movies. It's not actually about hacking, but Sneakers is a good movie. So there's too many intermediate languages. So one of the like sort of problems we have is there's actually a lot of these things. All right. So let's talk about some of the trade-offs that are in intermediate languages. First, you could have your intermediate language be very verbose. You could have it be very concise. What I mean is like, one native instruction could get lifted to many intermediate language instructions, or it could be lifted to very few intermediate language instructions. And that's kind of a trade-off you have to make. And generally, the more simplified the instruction set, the fewer the opcodes are, the more verbose it will be by necessity. Great example is like an AES instruction, right? So x86, you can actually have, there's AES instructions that will do AES encryption rounds in hardware, right? They're really fast and it's a nice feature. But if you want to now translate that to an IL that doesn't have like an AES instruction, well, that's actually a lot of IL instructions. That's a massive amount. And no IL that I know of supports that because ain't nobody got time for that, right? They use a thing called intrinsics for that, which we could talk about later if you want. And so you have this sort of trade-off. Like, do you add a lot of instructions in your IL? Well, the more instructions that we've added, maybe the harder it is to both lift, and also our analysis now that we're writing things to actually analyze the IL has to handle all of the ILs. And now we're back in the native machine code case, right? Where we had to handle all the native machine codes anyways. So these are like design trade-offs you can have to choose. And there's like several other ones too, right? Is it typed? Is it untyped? How do you deal with flags? The more flexible you are to problematic architectures, the more inherent trade-offs you have to make in terms of making your IL easy or harder to lift. So there's a whole bunch of these different design decisions. So here's a good example. This is, which one is this? This is, I want to say, I should look at my speaker notes. This is the Dynamics one, REIL, R-E-I-L. So this is one of the most verbose ILs you'll ever see. It actually, I think, only has like 12 instructions or something outrageous. So every instruction that you do is incredibly verbose. A test instruction lifts to 19, no, it's a lot more than that. 20, 30 instructions, right? And that's very hard to read as a human. But it turns out if you've used bindiff, you've used real in the background. It's actually using this for analysis, and it's a very powerful, effective tool. So for their purposes, that was totally fine. A very verbose lifting actually worked out okay. Conversely, this is a floating point load of the integer 1, which on, I think this is Binge's IL, but both Binge and Ghidra are the only two that I know of, for example, that have ILs that can actually handle this cleanly. Where they're like, yeah, it's just like, and it's a floating point number of a value of 1, right? Like they can just represent that in the IL kind of natively. So it's much simpler. You basically just couldn't/wouldn't do this in an IL that didn't have these explicit like instructions that could kind of handle it. All right, so let's talk about all of the different ILs that are out there. And I want to caveat this with, there's actually one new one that I've added to the source spreadsheet. So I'll share the slides after the talk. And this is actually a public Google sheet that I have that anyone can comment and I can update. But there's a new one that just got added to this from the, it's Elgato. No, it's not. It's Elgato. Elgato. I keep thinking like Elgato, like the game streaming company. It's not Elgato. It's Elgato. There's a new paper that just came out that has their own UIL for doing some binary translation stuff. But anyways, like this is like everything I could find that is an intermediate language designed for security or reverse engineering. So that's the big caveat. That's the big asterisk on this, right? Is that there are a lot of other ILs. Like every undergraduate computer science course that implements, a compiler might be implementing their own new IL. These are just the ILs that are, you see commonly kind of used in security and in reverse engineering. Except I'm actually cheating. I'm lying a little bit, and I'm wondering if somebody wants to call me out. Like, do you see something missing that I might not be including that you would have expected to see on this? I'll give you a second. Maybe I'll go get a drink of water to see. Yep, Grant's got it. Ooh, all right. Now, do I give him credit or do I wait and see if anybody else can figure it out too? He already figured it out too. Yeah, this is what's missing from this list is LLVM, right? So LLVMIR is absolutely used quite frequently in reverse engineering and in security analysis. But the reason that LLVM is not on here is because it has its own whole slide, right? So there's actually this many projects that just do native machine code to LLVMIR. And part of the reason there's so many is because this is actually really hard. It's easy to screw up. There's a lot of problems with this approach. A good example is that LLVM is typed, by which I mean you actually have to have type information in your LLVM, which makes complete sense when you're Clang and you're compiling code, which is what LLVM, right, is designed for. It's designed to go from source code and down to machine code. And so when you've got source code, like, of course you know the types. Like, you literally, that's like what your system does. It does things with the types and like emits machine code based on that. And so going forwards, you absolutely have types. In the reverse, well, you don't. Like, x86 is inherently untyped. Fun trivia question, try to like come up with x86 opcodes that have implicit types. There's a couple you could argue that might have them, but generally speaking, there are no types in assembly, right? And so certainly not complicated ones. And so what you'll see is that like when you've got to now translate your machine code back up into LLVM, you've now got to handle the type system. You got to like make your own analysis to recover types and then include that in the LLVMR, or else you're going to have like really poor kind of lifting. You're going to have not great results. And so this is a little bit like the chicken and the egg kind of approach. Like, you want an IL to be able to help you translate stuff to do type recovery, but then like you don't have it yet until you got the type recovery if you're using LLVMIR. So I think I would argue that LLVM is not a good choice to go from machine code straight to LLVM, but it's a perfectly fine choice if you've already gotten into an IL where you can do type recovery and do some stuff and then translate to LLVM, because there are a number of benefits from it. Okay, so I'm not going to talk about any more of the details of like all of those things, but I am going to show specifics, some of the more common or popular reverse engineering tools and their ILs. And I mentioned Dynamics and Real. Very few people probably even recognize that logo, but that bottom middle one is Real. Dynamics is the company behind BinDiff and BinNavi and VX Class. They were acquired by Google in 2014, 16, something like that. Halvar Flake is fairly well-known security researcher. And so we're going to talk about them just because of Real, and they're one of the good kind of security companies that have used used ILs publicly. The rest are probably fairly recognizable. We've got Redair, we've got Ghidra, LLVM is the dragon icon in the upper left, IDA, and Binary Ninja. The remaining ones. Ooh, here we go. I got a question. What about ILs for stranger architectures such as Hexagon? Yeah. So that's a very good question. And there's like a reason, for example, there's no Binja plugin for Hexagon is because it has weird properties, right? So there are definitely CPUs that have properties that make them more difficult to lift. And so that's why in this chart, like this last one is like, how easy do you make it to lift versus like how flexible are you at handling kind of weird stuff and extensible? And these aren't necessarily trade-offs. You might be able to have a well-designed IL that's easy to lift and also can handle problematic architectures. I think Ghidra is actually a pretty good example of that. But generally speaking, you'll see that that is the case. One of the questions I got the previous time I gave this talk was like, what does Binja's IL do badly or poorly? And I think my biggest like sort of regret or gripe or thing that I would change, and to be clear, I wouldn't change it because I am the worst developer on the product. The reason I can do talks like this is because I have much smarter people that are actually building the product. So Rusty, who's actually building the decompiler right now, did all the core IL design. He would be the person to do the actual work. But one of the things that we have noticed is there are some architectures, because the Binary Ninja IL design, it's very, very fast and easy to get most architectures lifted, like just much easier than a lot of other systems. But it comes at that cost that it's not as flexible for some of the kind of weird properties. And the way that Slade P code works, they've been able to do a really good job of like handling some weird stuff. So they do that pretty well. All right, good question from Grant on that one. All right, so I already talked a little bit about sort of the LVMIR, some of the kind of pros and cons. I do want to talk more about the pros. I talked about why there's some problems with it and why it's hard to do, but from the pros, there's a lot of analysis passes where you can do really nice things like a bunch of bug finding and a bunch of cool stuff you get if you have something in LVMIR. And so that's a reason what a lot of people would go to it. There's a big community of developers. And also, if you want to like re-emit, you want to recompile or translate a binary from one architecture into another, it makes total sense to go to LVMIR, right? Because once you've got it in correct LVMIR, you can re-emit to any other machine architecture that LLVM supports really easily. So that's a really nice feature. So you see a lot of the projects that I linked before that were lifting to LVMIR. Many of them were specifically for the goal of translation. So that makes more sense, right? They're translating from one binary to another. But again, there's like all those problems where you've now got to like single shot lift. And you got to implement all these features on a per architecture basis. So now you've got to implement your stack tracking, your SSA, your data flow, or other like forms and all this analysis, like kind of per every architecture, because you've now, or if you don't, you've actually sort of secretly internally got your own IL essentially that you're lifting to at that point. And then you're not one-shotting to LVM, you're going through something else, which would be the way to do it if you were going to do it. And it's not really designed for translation. All right, so microcode. Microcode from IDA is really cool because people have been using microcode for years, ever since the Hextrace decompiler was released, and they just didn't know it. It was never exposed. It was never talked about. And so one of the few things that I'll take credit for as one of the Binary Ninja devs is that I think we've sort of like increased the conversation and discussion around this. In fact, I know a friend, Sophia, was giving a presentation at a conference about Binary Ninja's ILs several years ago, and two of the Hextrace developers afterwards walked up and they're like, hey, we've got an IL too. Like, what APIs would you want? How would you work with it? What would you want to do? And then since then, we've seen them publish the spec, and you can actually see APIs, and you can interact with their IL. Theirs is not a terrible IL. It was never designed sort of for human consumption. You can see it's not really the way that it's set up really meant for people, but it's fine. It's not crazy verbose compared to other ones, but they have like, so this snippet of code you can see gets translated to the below snippets. The thing that they do is that they have these maturity levels, like a maturity model, which are kind of like these analysis passes that will simplify and improve the IL. So you notice it gets smaller. So it's the same IL, but they're actually having another pass that will sort of translate and rewrite the IL in a more efficient form. And so I think this comes down to like actually just like an if statement. On a dereference, maybe I forget. Oh yeah, that's that jump C is being folded into it. So yeah, you get like this really simplified thing, and then that gets parsed into the CD compilation. That's the final step before that happens. ILFAC has actually given a talk publicly where this content comes from. You can see more about their design. No, before IDA released this IL API, oh, you still can't write to their IL. So Grant's question was, before they released that API, could you lift, like, could you write your own processor module for IDA and get it to go through IL? No, you couldn't before, and you can't now, because they sell you a decompiler per architecture. So like you cannot add on to their decompiler and add support for an architecture that you want to lift. Yeah, and that's one of the biggest differences between IDA and Binja and Ghidra, is that if you implement in either Ghidra or Binja, like the one base IL, like all the other stuff just happens automatically. You get a full decompiler, right? So you can add on an architecture to support pretty easily. So yeah, like again, part of the reason that they didn't do this is they built their, I think we have the benefit of hindsight, right? Like they built their decompiler 15 years ago or 10 years ago or whatever. And so like, you know, some lessons learned that we could take advantage of. Although arguably Ghidra also was written at least that old and made better choices, I would argue, in terms of design for decompilation than Hextrace did to some degree. But the Hextrace analysis and the microcode, I don't know how old microcode actually goes. It might predate Hextrace significantly, may have been built into IDA internally. It's hard to say. So I'm not talking about Redair too much because I just have it here because a lot of people like it, and that's unfortunate. It has a really, let's see, I had to be careful. All right, there's some things I like about Redair. I like the command line, the fast interaction. It's open source, which is always nice. But their IL design in particular, their analysis design is really poor. It really doesn't work very well. It's very hacked together. A great example is I just saw a talk earlier. I was catching up on some old talks from Maddie, who's on Project Zero now, and she was talking about testing Diaphora, BinDiff, Radiff, and Darum Grim, and she ran just like a simple test, and it took like a couple minutes on BinDiff, and it took like a little while on, is a huge Redair fan in the audience? All right, good. Fight me afterwards. We'll have more of a talk about like the technical flaws of Redair. And Redair has a lot of huge fans, but anyways, go watch Maddie's talk where RADiff2 takes 9 hours to analyze one library and then gets it wrong. Like it gets it completely wrong. It's just not even correct at all. It couldn't do the one thing she wanted, which was like, tell me the two functions that change between these two versions of the library. And both Diaphora and BinDiff were able to do that. Although I think Diaphora had like only got one of the two. But like, Radiff was just like, yep, they're both totally new functions. And it's like, no, they're not at all. They were the same function with just a very few small basic block changes. So anyway, there's also like actually several different ILs built into Redair, and some ILs are designed for computers because they're easy to parse, and some ILs are designed for humans because they're easy to read, right? So like Binary Ninja IL was one of the very few that was sort of like had readability as one of its design goals. So from the beginning, we wanted you to be able to use the IL as a human and actually have it be usable. So you can switch between our ILs and they're actually like readable. Redair has it designed for neither because it's string based. So therefore, it's not for computers. You'd use like an actual structure or an object that you could parse more easily. You wouldn't have to like string parsing is relatively slow, but like it's also a postfix notation, so it's not also good for people to read. Anyway, I try to be nice. P-code, Ghidra. See, like it's open source, and I can say nice things about it. P-code is fairly well designed. As I've said several times, I think that P-code for the most part, it's concise. But it's also still readable. The way the SLA definitions work is fairly straightforward and fixable. They support a lot of architectures. My only real complaint with P-code is that you get like one shot. Like it's like the SLA definition, which you don't really interact with from an API perspective. You've got P-code and you've got decompilation. So there's a lot of actual analysis that happens between there. It's kind of in the black box, the decompiler portion of Ghidra, which is C++. It's not actually black box, it's open source. But what I mean is you don't have access to any of the data flow, any of the information internally that may have been necessary to generate that decompilation. And so the Binary Ninja's approach, which we'll see in a second, like it explicitly exposes these sort of intermediate stages of analysis. It's a very conscious choice. So that was my only real kind of nitpick with Ghidra. I think they lost out an opportunity to do that. But otherwise, it is probably the IL I would use if I wasn't using Binja's ILs for something. Real, I already mentioned, is 17 instructions, not 12. It's super verbose, but again, it gets the job done. Okay, so here's an update to my premise. No IL is perfect. Translations between ILs are therefore fundamental, and because like different ILs have different properties, the answer is, well, then just use lots of ILs, right? Like that actually is a reasonable answer because you can actually translate between different ILs much more easily than you can lift straight to a different one. So I actually think that like that's a reasonable thing. And you do see people translating on top of other ILs. It's a much easier process. But that's also why, this is the marketing pitch. This is why we designed Binary Ninja's ILs to be the way it is. We actually have all of these ILs as publicly exposed, except for the ones in the dark green at the very bottom. Those are the ones that are currently in testing. I'll show you shortly. We're tree-based. It's a family. I've talked a lot, I feel like. So if you guys have any questions, it's like, and my office actually heats up if I keep the door closed too long. So it's a little kind of keeps me from talking too long. So feel free to throw out some questions if you got ones. But let's look real quick. So this is assembly. And you'll notice one thing that I'm doing differently is I've got a much larger chunk of code on the screen than any of the other samples from other ILs. Because Binja is explicitly very concise when it produces its ILs. Are meant to be read by humans, and therefore you don't want it to be like pages of IL for one instruction, which again was just one of our design goals. It's not a bad thing for the other ILs that they don't do that. It's just wasn't part of their design criteria, right? So assembly, full screen so you can see a little bit better. I'll share the slides afterwards. Low-level IL, and it actually gets a little smaller, you'll notice, or actually stays about the same size, so it's not like any more verbose. And it's pretty readable. It's sort of a generic kind of notation. There's that one. And then there's medium level IL, which is even kind of smaller now. It's getting a little bit tinier. And then high level IL. High level IL, I'm actually cheating. This is the entire function. I was only looking at the first like quarter of the function. This is actually a little snippet of high level IL, but I'll show it like for real in a second. There's that. So here are sort of like some of the new high level IL opcodes. You can actually see this in advance. Folks may not realize, but all of the Binary Ninja API is open source. And so like when we're working on test features and test branches, the API portion of our commits still are public. So you can see even before we've released some of our test branches, you can see branch names and you can see, so the test branch commits where high level IL is updated in the API repo, you can actually see these different instructions. So if you're into Binja scripting and you want to learn more about like what are the new IL instructions coming along with high level IL and the types, you can check that out there. Okay, so why are there so many? XKCD summed it up well. Situation, there are 14 competing standards. 14, we must develop the universal standard that covers everyone's use cases. Yes, and now we have 15, right? So like that's basically what's happened. That said, there's actually a lot of good reasons, right? So I mentioned a lot of design trade-offs, and so there's good reasons to invent the new IL. You might want to invent the new IL because it doesn't support the language bindings you've got, or because there's no architecture lifting for the support you've got, and you don't want to like relearn the new IL, or it has features that are missing, and it just doesn't quite kind of fit your use case. That said, there's a lot of bad reasons too. So not invented here, it's like, well, I didn't write it, therefore I don't want to use it. Like that's sort of bad for the community as a whole. Every time you invent a new IL, it's just now yet another thing that like nobody is, like everyone's going to get like mediocre ability to use different things as opposed to just a few really high quality maintained things. It's especially true, unfortunately, like of open source projects that are kind of like one-off and abandoned. Another good reason is lack of awareness, which is one of the reasons I'm giving the talk, is to try to like show, look at all these ILs. If you're actually considering doing some IL analysis, check these things out. You should look at each of these. You might find the one that already has all the criteria you want, and then you could contribute to it and improve it as opposed to just making new one. And finally, the sort of publish or perish in academia is also partially to blame, where you're incentivized not to improve an existing thing, but to make your own new thing that's better in all these different ways. And so a lot of the research comes out of academia tends to be focused more on new stuff. All right, so questions to ask your IL before committing. I'm running close to out of time, so I want to move to the demo section. And then I have some bonus slides with some resources and stuff, which I'm not really going to cover. Yeah, you can see that in the slide deck if I share it. So let's stop for a second. I'm actually going to get a glass of water because I am actually getting thirsty. So you guys can think about any questions, put them in chat, and when I come back, we'll check out and see what your questions are, and then we'll move on to the demo portion where we're going to like actually show off Binja's decompiler, and which is like a new thing that's not yet public, but will hopefully be soon. So if somebody gave me $1 million and said, go design the IL to end all ILs, I think what I would do is I would do something a little bit like Binja's, right? I would have a stack of ILs, but what I would really focus on is designing ILs that you can translate between. Because again, I think that like ILs for different purposes make sense, but I would specifically design sort of a specification and an ability to translate between ILs so that even if my IL design didn't encompass your use case, you could later on adapt your problem to translate into my ILs and maybe go between different ILs. So that way, if you wanted to write your IL for, and I don't know what this looks like exactly, right? Like that's kind of what makes it a hard problem and open kind of question. But I think that really focusing on that translation layer, there actually, so Sergey Bradas, who is one of the people behind like POC or GTFO and a lot of the weird machine research over the years, is a DARPA PM right now. And he's been talking about this for a little while of like improving decompilers and translations between different ILs. And ironically, he actually launched a program called AMP just recently, which I think is like, it's been in like, the proposals are done. They're just selecting they've selected the folks and they're like starting the contract in the next couple months, I think. But it's not actually about that particular topic. So I don't know if he's got another one. Like you could kind of use, there's some stuff about translations of ILs that may come as a result of that research, but it's not really the main point of it. So I think that's one interesting area. I think the cool thing to do there is, there's a lack of quality in a lot of ILs, and what I mean is like it's just really easy to write bugs into an IL because it's a lot of tedious work, and so you see a lot of like just translation errors. And so I would like to see like a really nice test framework where you could validate that your IL is correct, and I think that would be really useful to improve just the state of ILs. And you could do that with emulation. So one of our eventual goals for Binary Ninja is to like emulate our IL in such a way that we can take like things like the CGC test corpus, run a binary where we know what the expected results are, and we do it natively and verify it, and then we can run it in an IL emulator and actually verify that the results are the same as a good way of sort of testing to find bugs in ILs and lifting. I think that would be an interesting thing too. Is it practical to use ILs to analyze embedded software firmware where the hardware becomes a major consideration? Yeah, I mean, I certainly think it is. It depends on what exactly that hardware is, right? Is it a coprocessor? Is it an instruction extension where you've got a bunch of new instructions? Or is it just some like, memory bus that's like you can read and write and do some stuff? And so it kind of depends on the specifics, but I absolutely think it still is. And you've got a couple different choices at that point. You could take your IL, maybe adapt it to that specific hardware device. There's some times where that's appropriate, especially like I said, for specific instructions. You can extend most of the ILs out there, except IDA, to add support for whatever the instruction is. So yeah, I think you totally can. And then like the hardware stuff, it just depends. Yeah, like it depends on what the hardware actually is. Another question is, for IL emulation, how do you handle intrinsics? Do you require a native emulator at that point? Yeah, you have to kind of stub out intrinsics or a separate emulator like syscalls and stuff like that as well too. You got to wire up something else to do that. So an intrinsic is, I mentioned that word earlier, and Grant asked about that again now. And intrinsic is essentially like that AES instruction, right? Like you would treat that as an intrinsic. You're not going to necessarily translate your IL one-to-one into exactly like a set of other ILs. But what you can do is say, well, I know what this instruction does. I'm just going to write some Python to like do whatever it does and give the result back. So when you have an emulator, that's how you have to kind of handle some of those very specific weird stuff, is you don't necessarily translate it to the IL and then emulate the IL. Rather, you just sort of stub it out and you're like, yeah, call this other function, you do it. You could also use intrinsics just to say like, well, I don't really know what this function does, but I know it reads this, writes this, and I don't know what it writes or what it reads. I just know it changes these things, and you can use that to help your taint analysis and some other stuff. So intrinsics are useful for that. So yeah, the answer is like you have to build intrinsics into your emulator to handle whatever it is if you want to get. It also depends on what level of fidelity and accuracy you want. Like maybe you're okay if your function fails. You may just like throw out test cases where you hit like an intrinsic you haven't handled yet, right? And then you could just validate your instructions that you lifted for the other ones. That's one way to handle it. So it depends on the accuracy. Jeremy asked if ILs are used in other areas of computer science beyond binary translation. Probably. Certainly, again, compiler design is the main one that I know of that they're used heavily in, and sort of language design, even in actually a good example is like browser JITs, right? For years, JavaScript was getting faster and faster, and then they started implementing JITs where they're actually compiling JavaScript into native machine code to make it run faster. Before they did that, they were actually translating the JavaScript into intermediate languages and then emulating over the intermediate languages. And so you see a lot of browser JavaScript engines. Arguably, that's very similar to the compiler kind of like school of research. But yeah, you definitely would see them there. There's probably other ones too. Yeah, smart contracts. Oh, thank you. Yeah, there we go. That's another good one too. Which again is also somewhat related to the sort of compiler design, right? Smart contracts, well, no, the analysis of a smart contract would be kind of like similar to the binary analysis stuff. But yeah, smart contracts are just implementing this byte code, this virtual instructions that they're using to do computation for whatever purposes. Yeah, you've got your blockchain. Yeah, that's a great point. I need to remember that one for other examples in the future. Yeah, and so Grant's comment was about like the environment problem for symbolic execution is very similar to the emulation problem for ILs. Yeah, absolutely. I think there's a bunch of kind of hard problems. Yeah, there's a bunch of work that requires to be done. I would say it's hard as in it's a difficult problem to solve. It's just hard in the sense that it's like not always super easy. Or it takes a lot of work, right? Like you have to do a lot to make it quality. Okay, so thank you for those questions. I appreciate it. Now let's go to this. Does anybody actually care about this? Is anybody here actually excited about Binary Ninja having a decompiler? I'm really excited about Binary Ninja having a decompiler. And if everybody else is not, that's all right. Indulge me just briefly. But so this is the high-level IL branch of Binary Ninja. And it's so the most common questions we get about it are like, well, can I do stuff with the API over it? The answer, of course, is always yes. We do one public API, everything can run against. So I've got current high-level IL as my, function object for BBin. I could operate over, well, that's not a very interesting function. So let's go and, I don't know, let's find something. This is a random old CTF challenge. There we go. All right, so I can write some code and I can iterate over the high-level IL just like any of the other ILs. I can do the usual kind of stuff that you might want to, you might want to write some code to kind of analyze. But you've now got, and this apologies for this font size being small, but now you've got a high-level IL, which again, the good easy way to tell is like how abstract are we is how small does it get. I show this, but this is not actually how we expect most people will use it, because one of the nice properties of high-level ILs is again meant to kind of look C-like, and I say C-like because yeah, like it's just what people sort of expect. But again, I want to clarify, our goal is not to make C. It's not meant to be valid C. It's meant to produce something that's very readable and understandable. It just happens that most people understand stuff that looks like C. So if I actually switch to my linear view, and part of the reason that high-level IL is not even public yet is that Rusty is refactoring the linear view. So the way that it operates, the data structures, the APIs for it, it was a little bit hacked up. It wasn't as great as we would like. And so now linear view, you'll see if I hit I here and switch to high-level IL in linear view, I'm actually looking at the high-level IL for all of these functions. And so like I can break it a little bit if I scroll. There we go. You see that? Yeah, that's the bug that's being fixed right now. Basically, the fact that this linear view is kind of a hack. It works, but it's not great, and the percentage estimates and stuff are off. So that's what he's working on right now. But you can see, I mean, this looks a little bit like decompilation. This is not something I've tested a huge amount on. This is again like just kind of an old CTF binary that I like to pull up. One thing I will note is that this version, you'll see the strings are outside of these function calls. It's like an annotation. But if I actually hit A and turn them into a string object, it'll re-trigger analysis, which reflows things, which is one of those bugs I mentioned. Yeah, analysis is still going. Yeah, so all these like scrolling where it does, this is exactly the bugs I sort of expect. So yeah, I can make, if I make everything a string. Oh, I forgot. I have my I have a little snippet in my snippet editor, which is, where'd it go? Did it launch? Oh, it's off screen somewhere. That's great. All right, so let's kill that. I've got a window, and to be fair, this is my fault and my bug because I wrote the snippet editor portion of Binary Ninja. All right, let's try this again. All right, so I'll not try to do that. So let's see. Oh, let's look at this. So one of the things I like to show is this particular CTF binary. Why I have it up is because it uses calloc to allocate some structures, some space for some structures, and then does some structure stuff with them. So this is a little kind of like heap style CTF pwnable challenge, right? Where it's going to allocate some objects on the heap, and you've got to get like a heap exploitation land on it. It's like the very typical, like you get like a text menu of like, you've got records and you want to add a new record and delete a new, you know, it's like, oh yeah, it's a heap bug. Like you just know like 80% of the time that's going to be the case. And so in this particular one, like this is the function here that's going to do a lot with these types. And so I'm going to actually switch over into medium level IL view, just because this function isn't written up on the high level IL side of this branch that I'm running here, which is actually about a month and a half old. And then what I can do is I can see this EAX is equal to the result of the calloc, and I can just hit S here, and it just makes a structure. And so, because it's like, oh look, it's like an allocation function, and it's making something this big, so make a structure that big. So if I actually go to the types view now, and look, I've got some, scroll past it. Yeah, so I've got like this random struct. Like I don't know what's in it yet, but I know I got a structure about that big because it was the result of that calloc. And now I can see I'm like actually writing to offsets. Well, I can just select one of those and hit S2 and turn those into fields. And so if I go back to the types view, you can see I've actually created types, and by default it just makes it like in 32, but I could change the type, you know, here or there. I could give it names. Like one of these actually I think is I think this is like next and previous, like it's a linked list one, and that's prev. And so now I can look back and I can see that it's initializing into 0. And then this is a really kind of a cool bug. I thought this was actually a bug, but there's kind of, oh, I'm about to go over here on time. So let me hurry up and finish up, and then I'll officially end, and then we can just kind of fiddle around if y'all have time and want to. But I thought this was a bug because there's this other calloc down here, and it gets like the same structure. And so if like I call this like, you know, node or something, whatever, as a type for that structure, I was like, it's getting it down here too. Like how does, like, that's a bug. It just sees like there's another calloc and it's making it there. And it's like, it turns out that's actually the type propagation system actually seeing a reference from one to the other and therefore applying the type appropriately. Because it does, you know, initialize like the first one. This is going to be like the head of the list right here. And then these are going to be like nodes that are going to be inserted into the linked list down here. And so the fun part though, is I haven't even showed it yet, is if I switch over to linear view and then hit I and then scroll a little bit because the scrolling is broken. This is what we get for the decompilation, right? So you can see it's actually got some nice features on the, although, and actually that while true might actually be right. I was about to make fun of it as a bad control flow recovery, but that may have actually been a while true in the source code. Probably not. Or is it? Yeah, no, it might have been. It was probably just a while that as opposed to that. But anyway, so what some of the fun things are, like out of the box, we have for loops, which Geeter doesn't decompile for some reason. Like nothing is actually a for loop. It's always just like a counter that's separately checked and then skips out. Rusty was like, I don't know why they didn't do that. That algorithm took me 2 hours to implement. So I'm not sure why that is, but yeah, but that's high level IL, hopefully coming out soon. I want to kind of, y'all are welcome to leave now. I'll hang around and answer a few more questions or poke around with this if you guys want to see more or talk about a little bit more, but I don't want to make people, I mean, because I'm sure y'all are very busy. There's a lot of stuff going on right now. I'm sure you have many appointments and places to go. See, it's a joke, and I can't even get any feedback because, like, oh man, it's tough. Anyway, so thanks for having me. If you guys want to leave, you can. If you have any questions or you want to see more, I'll happily do more. Or we can just stare at each other too. That's fine too.
Bye, Jordan. I liked it.
Yeah,
thank you.
Jordan, is it okay if we all get on voice now?
Yeah, we can bring everybody on voice. Everyone wants to hang around and ask questions.
Nice talk.
Thanks.
Yeah, I saw